5C Gravity and Freefall. 5.9 The Gravitational Field. Of all forces, we are most familiar with gravity. We live with gravity from the time we are born until we die. Most of the time, we don't even think about it. It's just always there. It may surprise you to learn that every object exerts a gravitational force on every other object in the world. If this is true, then why doesn't everything just clump together into one gigantic ball of matter? Mainly because common objects such as chairs and lamps, or even jumbo jet airliners and large ships, can't exert enough gravitational force to affect similarly sized objects. Gravity is a basic property of all matter. After studying the moon's motions, Newton concluded that the Earth's gravity acting on the moon depends on just three quantities: the mass of the Earth, the mass of the moon, and the distance between their centers. By inference, he concluded that this principle must be applicable to any two objects. In words, Newton's law of universal gravitation says that the force of gravity between two objects is proportional to the product of their masses. Thus, if you replace one of the objects with one having twice the mass, the gravitational force acting between the two objects doubles. For example, the Earth's gravity attracts a 10-kilogram concrete block twice as strongly as a 5-kilogram brick. Gravity also depends on the distance, d, between the centers of mass of two objects. The factor is 1 over d squared. So, if you double the distance between the center of the Earth and the brick, the resulting gravitational force on the brick is only 1/4 of the original. For this reason, gravitational force drops off very rapidly with distance from the Earth. A typical 9th grader weighs 602 N, 135 lbf, at the Earth's surface, but less than 0.2 N, 0.7 Oz, at the distance of the Moon's orbit. Since gravity is a field force, it extends outward indefinitely. It is theoretically possible to calculate the weight of an object due to the Earth's gravity at any distance from the Earth. However, the gravitational force diminishes so rapidly with distance that human-sized objects beyond the orbit of the Moon are essentially weightless with respect to the Earth. At even farther distances, other gravitational forces, such as that from the Sun, become more significant than the Earth's gravity. 5.10 Freefall. For nearly 2,000 years after Aristotle, teachers and students of science believed that the speed at which an object fell to the Earth was proportional to its weight. They held Aristotle in such high regard that it wasn't until the 16th century that anyone actually tested his idea. Galileo was a professor of natural philosophy at the University of Pisa in the state of Tuscany, Italy, when he began to question this ancient view. According to a popular story, Galileo dropped different-sized cannonballs off Pisa's famous Leaning Tower to disprove Aristotle's theory. It's more likely that this story was based on a thought experiment that Galileo described in his papers. He imagined two small equal weights dropped side by side from the same height at the same instant. According to Aristotle, they should hit the ground at the same time. Next, Galileo imagined connecting the two weights with a very light loose chain and then dropping the weights again with the same results. In his mind, he repeatedly dropped the weights after shortening the chain for each drop. Eventually, the chain was so short that the two weights were essentially a single mass, weighing twice as much as either original weight. But the doubled weight would fall in the same time as a single weight. This would disprove Aristotle's principle, which predicted that the doubled weight would fall a given distance twice as fast as the smaller weights. In his actual experiments, Galileo rolled balls down graduated wooden ramps to slow down the rate at which balls fell. He observed that metal balls of different weights rolled down the ramp in the same amount of time. He also discovered that the balls accelerated as they rolled. The acceleration was the same, within his ability to measure, no matter what the size or weight of the ball. Following Aristotle's reasoning, the larger, heavier balls should have rolled to the bottom of the ramp first, since they were more motivated to reach the Earth's center than lighter balls. Galileo also observed that the larger an object's surface area was in comparison to its weight, the more air resistance affected its motion. You can demonstrate this yourself by using 2 sheets of paper in a drop test. Crumple one of the sheets into a compact wad. Drop the two pieces of paper at the same time with the uncrumpled sheet horizontal to the floor. The crumpled wad will land first because its surface area compared to its weight is much smaller than the surface area of the flat sheet having the same weight. Air resistance friction on an object moving through the air significantly affects the rate of fall of bulky, low-density objects. Objects that fall due to gravity alone with no other forces acting on them are in free fall. An object can experience this condition only in complete vacuum where there is no air resistance. Objects in free fall change speed with a constant acceleration regardless of their masses. Objects that have more mass have greater gravitational force acting on them. But because they have more mass, they also have more inertia. A larger force acting on an object with a larger inertia produces the same acceleration as a smaller force acting on an object with a smaller inertia. The two effects exactly cancel each other out. 5.11. Gravitational acceleration and weight. Careful experimentation at many locations all over the Earth has demonstrated that the average gravitational acceleration g at sea level is about 9.8 ms, 32 fts. This value is acceptable for any place on the surface of the Earth. The discovery that all dense objects accelerate at the same rate regardless of their masses has important practical applications in physics. Let's look again at Newton's second law to see how this information can be useful. We know that the Earth exerts a force on all objects at its surface. We call this force weight, W. We know that all objects have mass, m. And we know that all objects have the same gravitational acceleration, g on Earth. When you substitute these quantities for their equivalent symbols in the formula for Newton's second law, F equal m times a, you get W equal m times g, where W is the weight of an object in newtons, m is the mass of the object in kilograms, and g is gravitational acceleration, a constant, in meters per second per second. The product mxg results in the SI unit kg m secant square, or newtons. The weight formula derived from Newton's second law is a convenient way to calculate the weight of any object quickly, given its mass. Recall that a law simply describes relationships among measurable quantities. It doesn't try to explain them. So don't make the mistake of assuming that an object must be accelerating in order to have weight. 5.12. Free fall and distance. Imagine that you are a missionary radio technician making repairs to the top of a 54.9 millimeter radio tower on the island of Carriacou in the Caribbean. You accidentally drop a bolt. How far does the bolt move each second it falls? How fast is it falling when it hits the ground? Answers to these questions involve the dynamics of free-falling objects. Gravitational acceleration near the Earth's surface is 9.8 mrs2. That is, the bolt's downward speed increases 9.8 rs for every second of free fall. After the first second, the bolt would be falling 9.8 ms. After 2 seconds, it would be falling 19.6 ms, 2sx 9.8 ms2. After the third second, it would be falling 29.4 ms, 3sx 9.8 ms. The increase of speed follows the formula for free fall. V equal g times delta t, where v is the free fall speed in meters per second. G is the gravitational acceleration in meters per second, and delta t is the total elapsed time of free fall in seconds. Knowing how fast the bolt is falling allows you to calculate how far it has fallen in a given amount of time. You can calculate the distance traveled by a moving object using the familiar equation, distance equals rate multiplied by the time traveled, or dE equal average v times delta t, where d is the distance in meters, v average is the average speed in meters per second, and delta t is the elapsed time interval in seconds. When an object has constant acceleration, as in free fall, its average speed during an interval is just the sum of the initial and final speeds in the interval divided by 2. During the first second of free fall, the bolt's initial speed is 0 meter per second, and it accelerates to 9.8 meter per second. Its average speed during the first second is 0 ms plus 9.8 ms2, or 4.9 ms. The bolt falls 4.9 ms x once, or about the 4.9 in the first second. Between 1 and 2 seconds, the bolt's average speed is 9.8 ms plus 19.6 ms by 2, or 14.7 ms. The bolt falls 14.7 meter during the interval, 1s to 2s, for a total drop of 19.6 meters. You can do the same analysis for every 1s interval during the fall of the bolt, ignoring air resistance. The total distance the bolt travels is the sum of the distances covered in all the 1s intervals. The table below summarizes this problem-solving approach. Since the radio tower is only 54.9 meter tall, the bolt will hit the ground sometime between 3s and 4s after the technician drops it. When objects accelerate at a constant rate, as they do in free fall, they experience uniform acceleration. Galileo observed that the distance an object moves during uniform acceleration is proportional to the square of the time interval. Physicists, since his time, have confirmed his observations and have developed a formula that relates distance, acceleration, and time. D equal half a times delta t square. This formula is valid only for cases of uniform acceleration such as gravity. For an object in gravitational freefall, the formula becomes d equal half g times delta t square, where g is the constant acceleration 9.8 ms. This formula is valid for any object starting from rest, dropping vertically in free fall, if air resistance is not significant. 513 Free fall and air resistance. In our discussion of free fall, we have neglected air resistance to simplify learning the concept of free fall. But in the real world, falling objects do encounter air resistance. Though air resistance complicates our scientific formulas, it isn't all bad. In fact, no air resistance would generally cause problems. Air resistance is a form of friction called drag. As a falling object's speed increases, drag on the object increases, exerting a force opposite to the direction of its fall. This force opposes the force of gravity on the object, its weight. This reduces the net force, accelerating it toward the ground. The falling object still accelerates, but at a decreasing rate. Eventually, if the object can fall far enough, the drag increases to the point that it equals the object's weight. The net force on the falling object is zero. According to Newton's first law, when the net force is zero, its acceleration is also zero. With zero acceleration, the object's speed is constant for the remainder of its fall. Physicists call this constant falling speed terminal velocity. The value of terminal velocity depends mainly on the object's cross-sectional area compared to its mass. A small, compact, dense object has a much higher terminal velocity than a broad, light, low-density object. These factors greatly affect things designed to fall through the air, like parachutes and ballistic missile warheads. The purpose of a parachute is to slow a falling human or space probe to a speed that will avoid injury or damage on landing. The terminal velocity of a parachutist needs to be very low. The chute is made of light. But strong materials to provide the necessary amount of drag, on the other hand, engineers design a ballistic missile warhead for exactly the opposite purpose. Heavy, extremely dense, and having a narrow conical shape, it produces the smallest drag possible. It has to fall through the atmosphere from the edge of space quickly to minimize the effects of wind and to avoid interception by anti-ballistic missile defenses. 514. Using Newton's laws to solve problems. How can we use man-made forces to transport people and things between floors of tall buildings against the force of gravity? The obvious answer is the elevator. Elevators have been in use since ancient times, including at the Colosseum and other amphitheaters in Roman times. Animals, water, or even people powered these elevators. With buildings growing taller in the 1800s, people needed a reliable elevator to move loads between floors safely. Early elevators were dangerous because they had no safety mechanism in case the supporting cable broke. Elisha Otis solved this problem in 1852. He worked for a New York furniture company that manufactured beds. His company needed an elevator to hoist heavy equipment safely to the upper. floors of its factory. He invented a device that stopped the downward motion of an elevator in the event that its cable or lifting machinery broke. His first device consisted of mechanical latches that engaged rails on both sides of the car whenever the cable failed. This invention prevented loss of equipment and, even more importantly, loss of human life. He showcased his invention at the 1853 New York World's Fair by staging a demonstration at the New York Crystal Palace. He rode his elevator to a dizzying height and then had a helper cut the supporting cable with an axe. The gathered crowd gasped at and then applauded as the safety mechanism locked into place, stopping the elevator's fall. He installed his first passenger elevator a few years later in a New York City department store.